Okay, class. So this lecture first, we're going to go back over homework 5, which we kind of missed last time, and so I'll do that now. So homework 5. Uh, okay, so problem 1 was pretty straightforward. You were to show the units of effective mass, which is root 2 m star kt over pi h bar squared to the 3/2. And by now, I'm sort of hoping you're very fluent with the idea that kt is energy and h bar is energy times time. And so this goes as kilograms, and this joules, and h bar is energy times time. Remember, that comes from the energy of a photon is h times frequency. So this is joule squared second squared. And so 3/2. And so that becomes kilogram over joule second squared to the 3/2. And then you can do it, a few different ways, but the easiest way usually to do these things is to think back to the formula for kinetic energy, 1/2 mv squared. And so realize that joules is kilogram mv squared meter squared per second squared to the 3/2. And so those cancel out, and those cancel out, and that becomes 1 over meter squared to the 3/2, which is 1 over meter cubed. Which is what we were trying to show, which is that the effective mass is basically a density, a carrier density. So it's like particles per unit volume. So particles doesn't have a unit, and so it's just 1 over volume. All right, so hopefully that went very smoothly for everyone. Okay, and I think I can just erase this. Problem 2, you were to calculate the intrinsic fermion. And so if we draw our conduction band and our valence band, and let's put a Fermi energy somewhere here, EF. All right. So you know by now, I mean, it should just be second nature, that n is n sub c e to the negative ec minus ef over kt, and p is n sub v e to the negative, think about a negative of that, ef minus ev over kt. So that's always true, meaning it doesn't matter what the doping level is. And so the problem was to calculate what the intrinsic Fermi level is, which is the Fermi level when there's no doping. And so let's label all these I here now. And then if it's intrinsic, meaning no doping, then, there's no acceptors or donors is equal to 0. And so, go back to our charge neutrality equation. Oops. But those are 0 and intrinsic, so P equals N. Which of course makes perfect sense, right? Because if there's no doping, any electrons up here left behind holes down there. And so now we just do the math. I have this wall here. I'm trying to like scrunch myself. That's why I tend not to use this little part of the board here. let's go on. So if P equals N, then basically NV e to the negative EFI minus EV over KT is equal to N sub C e to the negative EFI minus EC over KT. Now what we do for convenience is we go well, we just take the ratio of this. So NV over NC is equal to e to the negative EFI oh, what did I do here? I put that backwards. EC, sorry. EC minus EFI over KT over e to the negative EFI minus EV over KT. And so that's equal to just canceling out a few things. E to the, let me do it the way I did it in the handout. So basically, this one, you bring it up there, and there's 2 now. So it's e to the 2 EFI over KT. And now, the EV is positive, and when you bring that negative EC down there, that becomes positive too. So NV over NC is equal to, putting that all together on one exponent, e to the 2 EFI over KT minus EC plus EV over KT. All of that in the exponent. So now we just take the logarithm of both sides. So the logarithm of EC over EV, NV over NC is equal to 2 EFI over KT minus EC plus EV over KT. And we're solving for EFI, so now let's put that on the other side and multiply times KT, divide by 2. So EFI is equal to, rearranging this, KT over 2, so it's equal to EC plus EV over 2 plus KT over 2 logarithm of NV over NC. And, you know, that's the answer. I asked you to put it in terms of effective mass, and unfortunately I erased problem 1. But from NC and NV both go as m star to the 3/2. So this is equal to EC plus EV over 2 plus kt over 2 logarithm of mv over mc to the 3/2. But remember the rules of logarithm. Logarithm of a to the x comes over here. So that's ec plus ev over 2 plus 3/4 kt logarithm of mv star over mc star. And so that's the final answer. Now, what you see is that, and you know, this sometimes is not entirely apparent. This is the conduction band energy plus the valence band energy, the sum over 2. So that's the middle of the band gap. If you have trouble seeing that, just put the zero of energy at EV and think about it. Then it's EC over 2, which is the middle of the band gap. So, you know, if I draw right in the middle, so I mean that's EC plus EV over 2. All right. This is if MC star is equal to MV star. And if you think about it, that makes perfect sense because the bands are symmetric, and so if n equals p, it should be right in the middle. Now, if MV star is larger, and now let's go back to K space. So let's say that MV is larger. Now remember, a larger effective mass, right? And I'm not going to write down all the equations going back, but remember, you know, you go back to your energy is h bar squared k squared over 2m. So if m is bigger, the curvature is smaller, and so the band is flatter. So this is for MV star is larger than MC star. Which, if you think about it, we'll talk about the quiz in a little bit. Another good pictorial quiz problem is, okay, draw the, you know, whoops, I should have put that. In fact, maybe I'll do that, give it away. You know, I could make up 2 slides now, showing more curvature in the conduction band than in the valence band, and draw the intrinsic Fermi level, and then 2 slides. We could do the same thing that we did in the quiz. But basically, going back to the equation, if the effective mass is larger, then the argument in the logarithm is greater than 1, and so that's a positive quantity, and so basically EFI goes up. Now, the fact that EFI is going up, if the valence band has a higher effective mass than the conduction band, really should be something you should be able to piece together sort of pictorially. Because if you think about it, then, okay, and the way to think about it is this. Okay, draw a little decay. And remember, for for 3-dimensional materials, what I'm really drawing here is k sub r, the radius in k space. But if you think about it properly, and it's sort of hard to make a good drawing, but basically, now that dE is larger than that dE. Right? Now, with a constant decay, I have the same number of states, right? Because the states are spaced evenly in K. So that means that since dE is larger, the states per energy, G is of the conduction is smaller than G of the valence for more curvature. Because dE is larger, so for the same number of states, I've covered more energy, and so the states per unit energy has gone down with more curvature. Okay. You know, I try to think about that on the side, but basically, you know, you can remember more curvature means a lower density of states. Now, hence, okay, remember the, you know, n, for example, is the integral of fg dE. Okay, and so since the conduction band has a lower density of states, in order to have the same n as P, the Fermi energy must get closer to it. Because since this went down, that has to go up. All right, and sort of conversely, right, since the density of states is larger in the valence band, all right, remember P is basically the integral of 1 minus f, because that's the probability of a hole, times G, I should label these, of the valence band. And so, since that went up, that has to go down, and for those two to be equal. And so 1 minus f means the Fermi energy moves away. All right, and what I'm going to ask you to do, you know, sort of in the limitations of time for this lecture, is to go through all this pictorially, draw f, you've seen me do it and things like that, and, you know, come to grips with the understanding that in order for n to be equal to P, since G is lower here than here, the Fermi energy has to move closer to it. So you could have you could have worked that out qualitatively yourself, that if mv is larger than mc, then it should move up. Now here you have the equation, and so you see by how much it moves up, given a certain ratio of mv to nc, you take the logarithm of that. Now remember, when you take a logarithm, like the logarithm of 10 is what, 2 or something like that. So this becomes basically a few kT. And so this could be something like a few kT. Now remember, kT is 0.026 electron volts at 300 Kelvin, whereas this is, you know, somewhere in the order of 1 eV. And so a few kT is not a big value compared to the band gap itself. So we typically, you know, and you know, as we well, sometimes we just make the approximation that the intrinsic Fermi energy is in the middle of the band gap, even if, which is usually the case, the effective masses are different, because this is pretty small. Okay, so that's problem 2, and you know, again, I'd like you to go through this yourself pictorially so that you understand why, which is typically the case, the conduction band has more curvature, and therefore, and why that means it has a lower density of states. Okay, that the intrinsic Fermi energy must move up. Okay, now problem 3. And for problem 3, we went back, which I'm not going to rederive, that the Fermi energy for N-type material is equal to the intrinsic Fermi energy plus kT with nd over ni. Now, you know, we could go back and derive this again. I mean, this comes from everything comes from charge neutrality. P plus Na equals to N plus Nd. And so you can rederive this yourself, which I encourage you to do here. But it's sort of easy to understand and remember, perhaps, because of course, if Nd is equal to Ni, then it's essentially undoped, and the logarithm of 1 is 0, and so you go back to EFI. Now, remember also, though, this is an approximation for Nd is much greater than Ni. So it really isn't valid when you get, you know, at Ni. But that sort of, you know, clues you in, maybe mnemonically, to remember the equation. So now what I said was that okay, so if the effective masses are the same, then this becomes EF is equal to E gap over 2, because I put the zero of energy at. All right, now going back to this diagram. So this diagram basically draws EC, BD, and EC. And here I plot ND logarithmically, log scale. And this equation basically shows that, okay, here's the middle of the band gap, that this goes as a straight line over some range when you have a log scale here, meaning the log scale is like, you know, 10 to the 11th, 10 to the 12th. You know, I'm making up numbers here, but just showing you there's a log scale. All right, now, I could have asked on both sides here. I mean, basically, this limitation limits what can happen here, because basically, if Ni is over here, right, you have to be like, you know, maybe 5 Ni, you know, and Nd has to be like 5 Ni or something for this to be true here. And so, you know, that sort of limits it on this side, and that's why you can't ever draw this going to here, because for it to be there, Nd would have to be equal Ni, and so, you know, that won't work. And what I asked you to do is on this side the limitation is because, okay, these formulas we've been using, you know, our favorite formulas in the world, right? Okay, I'll just write the one for N. That formula is only works for EC is much greater than EF. All right, and you have to go back to, you know, because when this formula comes from the interval of Fg, right, from EC to infinity, but, you know, F is, you know, actually 1 over 1 plus e to the e minus EF over KT, and we approximated it as e to the negative e minus EF over KT, meaning that's much bigger than 1, the way around. sorry for getting a little messy here. You know, remember the Fermi-Dirac function is this, and when we calculated n to do, you see, if we had left it in this way, we couldn't have done the integral, because g, remember g when it's the square root of e over 1 plus e to the e minus ef over kt would have been kind of a one of these integrals you have to look up. But by approximating, this is much bigger than 1. Now, if that's, for that to be true, e has to be much bigger than e. It has to be a lot, you know, it has to be, wrote this wrong. EC minus EF has to be much bigger than KT. Okay, if E minus EF is much bigger than KT, then this is something to a large number, and so that's much bigger than 1. Now, and the reason why that turns into EC minus EF is much bigger than KT is because the integral starts at EC. So that's, you know, the first energy you care about. So this basically has to be much bigger than KT in order for all of this to be valid. And that was the homework problem, was to determine at what doping density that happens. So we can do that. You know, we basically figure out what that is. Now, remember what this equation is. This equation is that. So that basically means that EC, no, okay, so this is E gap over 2, right? Because I said it was in the middle because the effective masses were equal. And so basically that means that EF minus E gap over 2, let's just write it out. So it means that EC minus EF is much bigger than KT. So that's EC minus E gap over 2 plus KT over ND over NI. It's much bigger than KT. Now, I mean, remember, I set my zero of energy, you know, I set EV equal to 0 to write this down simply. So if EV is equal to 0, EC is E gap. Right, and so this means that E gap over 2 minus KT logarithm of ND over NI is much bigger than KT. And so we can turn this around, and so let's say that it's equal, you know, let's use 3. Okay, so we'll say it's equal to 3 KT, because 3 KT is much bigger than KT. By the way, 3 then, okay, if this was 3 KT, that would be e to the third, and e to the third is somewhere around 10, so that's kind of close enough. So just solving this equation then, we get that ln ND over NI is equal to, putting that either 7, is equal to E gap over 2 KT minus 3. And that's 1 over 2. This is at 300 Kelvin, 0.026 minus 3, and 1 over 2 over 0.026 is around 17, or 19, and so this you work out 16.23. So you just solve for that then. And I said Ni was 10 to the 10th, so that works out to 1.1 times 10 to the 17 over Cm. So, I mean, basically I solve for when this is 3 kT. And so that works out that for 300 Kelvin, the limit is 1.1 times 10 to the 17, 1 over centimeter squared, if Ni is 10 to the 10th. And then I said do it for 400 Kelvin, and so for 400 Kelvin, you know, ln of Nd over Ni is equal to E gap is 1 over 2. Now at 400 Kelvin, kT is 0.035. Just taking 0.026 and multiplying times 4 over 3. Minus 3. And so that's 11.29. And so 400 Kelvin, and V works out to 8 times 10 to the 14th. And that's because at 400 Kelvin, basically, this is 300 Kelvin. At 400 Kelvin, the slope goes as kT, so it does something like that. And so now, you know, if this is 3 kT, well, it doesn't work out right. It works out to 8 times 10 to the 14. Which, you know, perhaps a good exercise would be to take this equation and plot it versus Nd over Ni. That'd be another way to do it, is just graphically. And perhaps I'll do that. Well, maybe I'll ask that as a homework problem for you to just plot that. I mean, it's pretty simple, right? I mean, basically plot this equation. It's a straight line for kT of at 300 Kelvin and 400 Kelvin. You know, you have to, you can't start at Ni. I mean you could, it wouldn't be right. I mean, but just plot it as a function of Nd over Ni, and you know, just see graphically when it reaches a few kT. So that might be a good homework problem to do, to augment this. All right. Now is when I would ask if there's any questions, and we probably spend the rest of the class talking about the homework. But let's, you know, that's basically it. And so hopefully, if you go over it again, you'll get it good. It seems like my camera's moved a little bit somehow. Okay. All right. That's it for the homework, for homework 5. All right, now, oh, let's go over the quiz. And let's do the quiz this way. Let's just start first with the premise. You know, that Ni is less than Nd. I mean, that's what you were supposed to sort of realize from the diagrams. But so here's P and N, and you know, again, the main problem that those of you who got the answer wrong had was sort of this backward way of thinking about what happens to the depletion regions. For now, remember, well, I mean, I'll just write it down and draw it at the same time. Okay, this is minus xp, this is x equals 0, this is xn. And for charge neutrality, okay, xp and a is equal to xn nd. Because, I mean, you could put array here if you wanted, you know, I mean, that's basically Q plus sorry, Q minus is equal to Q plus. Because remember, when an acceptor atom becomes ionized, it accepts an electron, so it becomes negatively charged. Na is the acceptor atoms per unit volume. So to get the total number of acceptor atoms, right, you would multiply times the volume, which is A times XP. And same thing on the other side, when a donor atom donates an electron, it becomes positively charged because it lost that electron. And so you would multiply it times volume, which is XNA. And of course the A's cancel out. And so, so, you know, because, okay, now, okay, if you're not exactly clear, you know, why that's the case, I mean, it just sort of makes sense, right? I mean, you wouldn't have excess charge. I mean, the diode wouldn't be sitting there with you know, excess net charge. So let's just leave it at that. And so because this is true, if Na is smaller, XP has to get bigger. You can solve that equation if you want to see, but I think that just sort of makes it more complicated than necessary. All right, so, you know, I mean, I could have framed the question the other way. It's just that then you would have had to turn in a file in which you drew something, which would have been complicated. I could have said, Na is less than Nd, draw these two diagrams. All right, and that's this one, and then the other one is, okay, from the last lecture, what I told you is that when you forward bias the diode, all right, it leads to an excess hole concentration on the, because basically you forward bias it, you lower the barrier, and all these holes on this side go flung over that side, and so you have excess hole concentration, and this is Pn0. I'll just continue to draw it. And then on the, now, let's do our diagram. So Pn0, right? Remember, Pn0, we're out here in the equilibrium, you know, we're far away from the junction, so we're in equilibrium. So N times P is Ni squared, far away from the junction. So far away from the junction, out here, N is approximately equal to Nd. And so Nd Pn0 is Ni squared. So Pn0 is equal to Ni squared over Nd. All right. Now, we said that Nd is larger than Na. that means that Pn0 is smaller than Np0. I'm trying to flatten myself against the wall here. And P0, which is equal to Ni squared over Na. Okay, so, I mean, that's basically it. I produced a diagram. You know, I did the quiz sort of backwards, and then I started with this and then drew the diagrams. You were supposed to see this being less than that and understand that that meant that this was true. And in fact, almost all of you understood that, which is good. And then, because that's true, you're supposed to understand that the depletion region and the P side was larger. Okay. So that's the quiz. Now today, I'm going to explain why I drew this point lower than that point. So today we're going to understand that. I'm just trying to think if now's the time to jump ahead a little bit. Okay, let's do it. We'll do it now. We'll do it later. Okay, because it's kind of like, you know, everything goes up. So if NP0, the equilibrium electron concentration in the p side is higher, that means that N sub p, the injected electron concentration, P sub n, or what did I do? I wrote, yeah, this is n. N sub p, right, the injected electron concentration in the hole side is higher at the junction, at the edge of the depletion region, than P sub n, the injected hole. Now, okay, now we can actually kind of think a little bit more about this, because, and this is where some of you, the ones who got this part wrong, will maybe appreciate this, because when you got it wrong, as we went through in the chat session yesterday, you kind of got it wrong because you were thinking that, okay, you figured out from this, right, that that's true. And you go, okay, there's fewer acceptors, and then somehow you're like, okay, that means less is going on in the P side, and sort of backwards reason that that would be smaller because of that. Okay, so, which is not true. Okay, but you'll sort of appreciate this now. If Na is smaller, right, there's fewer holes on this side than there are electrons on that side. So it makes sense that when I forward bias it, right, I'm going to get more electrons because there's more electrons here than holes there. The electrons flooding, you know, that component of charge is going to be larger than the holes going over there because there's fewer holes to begin with. Get it? So when I lower the barrier, I get electrons and holes. If Na is smaller, okay, I get more electrons. So it all kind of fits together. This picture fits together with that, and that sort of reasoning. Okay. Now, I don't want to do too much of a review of diffusion, but let's go ahead and do it. Looking over here. Now, if this is dx, all right, and I'm going to make F. Remember, F is flux. That's proportional to dp dx. Now, F, right, is minus d dp dx. It's the flux of holes. And the minus sign is because, you know, when the slope is negative, the holes are going that way. Now, if you look at this, the slope here is bigger than the slope there. So that arrow is bigger than that arrow. All right, now what does it mean? Okay, it means that there's sort of, you know, holes recombining in there. And remember, flux is carriers per unit time per unit area. So F of x minus F of x plus dx is equal to the holes per unit time disappearing. Can't spell disappearing. Disappearing. So when is there? Okay. Okay, going away. I could have wrote going away. The holes per unit time disappearing. And you would have to put well, okay, so it's the holes per unit time per unit area. Because remember, this is carriers per unit time per unit area. So the difference in f of x and f of x plus dx is the holes per unit time disappearing per unit area. And that's equal to p minus pn0 over tau times dx. Now the reason why I sort of did this, because remember, p minus pn0, why p minus pn0? Because if p is equal to pn0, there's nothing disappearing, because the flux is the same everywhere. Well, there is no flux, so there's nothing disappearing. It's only when, you know, this p goes like that now there is flux, and so something has to be disappearing. So nothing's disappearing if p equals pn0. As p goes up above pn0, okay, then things start disappearing. And p minus pn0 has units as 1 over volume. So I'm going to multiply times dx to get 1 over area. And the rate of disappearing, so the rate of disappearing goes as the difference between p and pn0. You know, the higher p is above pn0, the larger the recombination rate. And it also goes as 1 over tau. That's why my camera keeps moving. It's the cat. I didn't stop doing that. But 1 over tau, because tau is the recombination time, basically a shorter time means a faster rate. All right, so I hope you can see that. And then, you know, we put this on the other side. F of x minus f of x plus dx over dx, right? Now, what is that? That's minus df dx. Right, going back to your first calculus class. And f is d dp dx minus, so the minus cancel. So d squared p dx squared is df dx. And that's equal to p minus pn0 over tau. And, okay, we rewrote that because we defined this d tau. So right, d squared p dx squared is equal to p minus pn0, where L is defined to be d tau, where L is what we call the diffusion length. And you can sort of, well, you can at least see it with tau, right? Because if tau gets bigger, that means the recombination time gets longer, so the length over which a carrier goes before it recombines should be larger, right? So it kind of makes sense. And you can figure out the units of this by going back here if you want to, and understanding the flux is 1 over time area. Just maybe another good homework problem. All right, well anyway, we sort of, you know, and this is diffusion theory, and it actually can be more complicated than this. Diffusion theory can involve generation as well as recombination, and various other effects can be going on. But for the diode, this is all you need to worry about. And again, a typical course might teach diffusion theory before doing diodes, but you know, I sort of chose to because now we have, you know, diffusion going on. So now let's figure out how we describe it. So the differential equation is this, and you know, I showed last time, and I'm not going to go over that again. That the solution of this is then P of x is Pn0 plus Pn minus Pn0 e to the negative x over, well, e to the negative x minus xn over L. Yeah, you can see that. In order to see that, okay, first of all, do it offline. Take the second derivative of this, and you'll see that it fits the equation. Because, you know, every time you take a derivative of this, you get a 1 over L, so you get a 1 over L squared. So you can see that. And also by the boundary conditions, you can see that if x equals xn, this becomes e to the 0, which is 1. And so this becomes Pn0 plus Pn, and so it becomes Pn at x equals 0. And as x goes to infinity, this part goes away and becomes Pn0. All right, so you can basically see that equation and understand that that's an exponentially declining whole, but it doesn't decline to 0, it declines to Pn0. Okay. Now, we're almost there. We're really close because we have our hole profile, and so we know how much diffusion is going on of holes, and so we know how much current. Because remember, current density anyway, is just F times the electronic charge. We'll walk through that again in a second. Right now, I want to focus on this guy here, P sub n. What is P sub n? All right. Now, here's where many courses and/or textbooks on solid-state devices might spend a lot of time discussing this and referring to band diagrams. This is one of these times in the course. Remember one of the other times, well, you know, there's been several times where you have to take things on faith a little bit. Remember, the other time was when we did band theory, we had to accept Bloch's theorem, which is, you know, that the wave function repeats with the space factor. and here, this isn't described as a theorem because it's just too easily makes sense. And I'll just write it down. So let's write it down and think about it. What is Pn? Pn is equal to Pn0 e to the EVF over KT. Remember, VF is the forward bias voltage. And I'm going to ask you to just accept that for this course, because really, you know, you could sort of draw pictures and talk about quasi-Fermi levels and the law of the junction, which is another thing you might hear about. But it really just kind of makes sense, okay? It makes sense because, okay, first of all, if you look at this, if VF equals 0, P, you know, then Pn is equal to Pn0, and we're back to our flat condition. So, you know, that's what's supposed to happen. And it makes sense that So it makes sense that this is Pn0 in front here. And it makes sense that as VF gets larger than 0, you're forward biasing it, the hole concentration here should go up exponentially with the forward bias voltage, because everything goes exponentially here to the lowering of the barrier. The lowering of the barrier goes as the forward bias voltage, all right, and because of, you know, basically the Fermi-Dirac function, then the flood of carriers going over the barrier goes exponentially as the lowering of the barrier. So it just makes too much sense, right, just writing it down for you to question it. And so, you know, just look at it and go, yeah, of course that's right. Now, there's an E there, electronic charge, because that's then energy, right? So, you know, don't get too worked up over that. I know it's unfortunate there's an E there, and that's of course, you know, E, right? Whereas this is electronic charge. Looking at this for a little bit, I mean, same thing over here. NP is equal to NP0 e to the EVF over KT. So they both go as e to the EVF over KT, which makes sense, of course. As you lower the barriers, you get electrons in holes. Because it goes as the equilibrium binary carrier concentration. If NP0 is higher, then this is higher. So I've just shown why, when you draw this diagram, if this is higher than that, then this is also higher than that. And it all fits together because if, you know, all of this has been drawn for n equals less than nd, I mean, you can do the same thing for the opposite, then everything will be flipped. There's fewer holes, so when I lower the barrier, I get fewer holes injected than electrons. So it all fits together qualitatively and makes a lot of sense. All right, so if I plug this in, then P of x is equal to, now let me just, okay, I'll just write this way, Pn0 plus Pn0, because the Pn there, times 1, times e to the EF over KT minus 1 e to the negative x minus xn over L. Where I just plugged in for Pn. And I pulled that up Pn0. Hey, those of you that know this stuff, right, you're looking here now and you're going, oh yeah, it's ringing bells. All right, now there's just a little bit left to do. And the little bit left to do is we want J for the holes. Now, what is J? Okay, remember J is charge per unit time per unit area, right? So that's just E times carriers per unit time. That looks unfortunate. Per unit area. That's not an exponent. That's E electron charge. Right? Just doing the units, right? Just carriers times charge, and you know, because the carriers are having a charge of an electron. And this is F. Wherever it is. Somewhere. No, here. All right, that's F. So J is just EF or minus E d dp dx. Sorry, cat. So we can get J directly from P by taking its first derivative. All right, now, let me see my time here. All right, okay, we'll finish up here. All right, I'll save till next time going through this more, because that way it'll be part of a review also, and so connect everything. I'm going to calculate J by doing this at x equals xn. All right, and I'll explain why that makes perfect sense in the next lecture. Basically, I'm going to use this slope. Now, if you think about it, because that slope is going down, J is going down, the diffusion current. Now that's okay because something is making it up. And I'll explain what that is. I mean, you may understand what it is next time. But basically, JP is going down and another component of J is going up. But at the edge of the depletion region, the only component of current is the diffusion current, J sub P. Okay? So I'm going to evaluate this at x equals xn just by taking the first derivative. So that's equal to, just look at it here, Pn0. When I take the derivative there, that gives me a 1 over L. The minus sign went away. And this one goes away because there's no derivative. E to the EVF over KT minus 1. And that's e to the x minus xn over L, but that's evaluated at x equals xn. So that just is equal to, and I forgot a d. And an e, using everything. E d Pn0 over L times e to the the nice thing about this is that it's really easy, right? Nothing is really that hard. I mean, this is the only part you have to kind of just accept. But it makes so much sense, it's easy to. You know, this you just sort of piece together, and you come up with the whole distribution, the excess whole, or the whole distribution, and then you just take the first derivative and evaluate it here, and that's why we did it that way, and it goes away. Now that's J sub P. J sub E is the same thing, right? The electron's over here. Now I do have to, okay, that's the diffusion for holes, and that's the diffusion length for holes. Okay, JE, same thing, E for electrons, and P0 over M electrons. Same thing. And so J is its own. Which, by the way, the minus sign's all worked out because electrons going that way is current going this way. So the answer is in the electronic current out, D sub E and P0 over LE plus D sub H Pn0 over LH Okay, we're going to stop there. Um, in the course notes, you'll see that we then do a little bit of manipulation here to gain a little bit more understanding about what's going on. But this is the answer, and importantly, it's some prefactor that's independent of voltage. See, voltage only appears there times e to the EF over KT minus 1. Of course, if VF equals 0, this is 0 because there's no current if it's 0. And this gives rise to what you're used to seeing. And so now you know where that comes from. All right, so we'll stop there for this week, and next week we'll pick up on this. We'll do a little bit of manipulation here so that you can sort of see a little bit more what's going on with that. And also go over why we did that and what else is happening so that that is true. And that's it. Okay, so that's it for this lecture, and that worked out just about right. And I'll see if I can figure out some homework to hand out. And tomorrow morning, well, this is today, so Wednesday morning we'll have our chat session. All right, thank you very much.